Well, if you weren't able to make it to the class on gravitational waves, here's some information for you that'll help you out with studying. So the first thing that we went over in class was about those Schwarzschild radius problems that I gave you a copy of, and there's a copy of it in Moodle. There's also a solution guide in Moodle, and then a little bit about gravitational waves and the largest gamma ray burst ever. And then right after break, we'll do class about the Milky Way, which is actually on the final unit exam. And but Thursday will be the Unit 3 test. That's on chapters 23 and 24. All right, so this is a quick review of calculating a Schwarzschild radius. For any remnant star, like a neutron star or a black hole, or really for any object, it turns out, there's a radius called the Schwarzschild radius. And this formula was developed by Carl Schwarzschild. And the Schwarzschild radius is equal to the product of 2 times the universal gravitation constant, which is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times the mass of the star, or whatever object it is, divided by the speed of light squared. You need to be able to use the formula and practice with a calculator so that you can correctly calculate a Schwarzschild radius for any star remnant. Could be for an active star, or it could be for a neutron star, but it's especially important with figuring out whether or not a star remnant is a black hole. So for instance, for our sun, the star that we orbit, it has a Schwarzschild radius. And if you put the universal gravitation constant, that's the 6.67 times 10 to the negative 11th. It's kilogram meter squared per second squared, or the unit really doesn't make a whole lot of difference for you. And then the mass of the sun is 1.99 times 10 to the 30th kilogram, and divide that by the speed of light squared. Now, the speed of light is 3 times 10 to the 8th meters per second, but the speed of light squared comes out to be 9 times 10 to the 16th meters per second, meters squared per second squared. Because anytime you square something in scientific notation, the base in the scientific notation gets squared. So for instance, 3 squared is 9. And then the times 10 to the 18th, 10 to the 18th squared is the same as 10, I'm sorry, not 10 to the 18th, but 10 to the 8th squared is the same as 10 to the quantity 8 times 2, which is 16. So the denominator in every one of these Schwarzschild radius problems can also just be 9 times 10 to the 16th meters squared per second squared. Anyway, nonetheless, if you put the mass of the sun, our sun, into the equation, you get a radius of 2,949 meters. So what does that mean? Well, the sun itself is about 700 million meters in radius, but I just calculated the Schwarzschild radius for the sun is 2,949 meters. That means that in order for our sun to be a black hole, which it isn't and can't be, all the mass of the sun would have to fit within that little black circle, the sun's Schwarzschild radius of 2,949 meters. Now, one solar mass of mass, or the mass of our sun, is not enough mass in any situation for a star to be a black hole. So most main sequence stars are not black holes. They don't have nearly high enough densities, like in the case of a neutron star. So since the Schwarzschild radius is a smaller radius than the radius of the sun itself, the sun is not a black hole. If you go to a more dense object, maybe something with a more mass than the sun, like a neutron star. So here's a neutron star that has a mass of about 1.4 solar masses. Or if you take the mass of the sun, multiply by 1.4, it's about 2.8 times 10 to the 30th kilogram. This is just a mass that I made up, but it'd be a very typical mass for a neutron star. And the Schwarzschild radius for a neutron star with about 1.4 solar masses is about 4,150 meters. That's a greater radius than the Schwarzschild radius for the sun. So it turns out the Schwarzschild radius just goes up linearly with whatever mass of the star happens to be. Well, neutron stars are very dense. So it turns out that this 1.4 solar mass neutron star may have a radius of like 11,000 meters or 11 kilometers, which is like somewhere around 7 miles or so. It's 1.4 times the mass of the sun with a radius of only 7 miles. That's pretty typical for very high density neutron stars. But I calculated the Schwarzschild radius for this star remnant A neutron star that could be the remnant of a supernova from maybe a supergiant has a Schwarzschild radius of 4,150 meters. So once again, the mass of that star doesn't fit within the calculated Schwarzschild radius. And the neutron star is a visible star, well, maybe visible in the ultraviolet or radio or something like that, but may not be visible to the naked eye. But nonetheless, the star is not a black hole. It doesn't have a strong enough gravitational field to bend space-time to create one of these black holes. So what about a black hole? Well, the minimum mass for a star or a stellar remnant to become a black hole is about 3 solar masses. So here I took and multiplied the mass of our sun by about 3, and it's slightly over 3 solar masses, or 6 times 10 to the 30th kilogram. So the mass of our sun is 1.99 times 10 to the 30th. This is 6 times 10 to the 30th. If you had about 3 solar masses, the Schwarzschild radius is 8,893 meters. So what if this 3 solar mass stellar remnant has a radius of 8,893 meters or less? Then the object happens to be a black hole. So in this little illustration, the black hole is illustrated by the yellow circle, and the Schwarzschild radius is 8,893 meters. That's the size of the black circle. So all of the mass of the black hole may actually exist or reside within the yellow circle, but the Schwarzschild radius is larger, or the size of the black circle, 8,893 meters. And that outside radius, the outside of the black circle, happens to be the location of the event horizon. So any mass or light or any kind of energy which crosses that Schwarzschild radius, the size of the large black circle in the diagram, is kind of like past the point of no return, and it's well within the event horizon, and then that mass can accrete onto the mass of the stellar remnant, the mass of the black hole itself, which can be represented by the yellow circle. Anyway, so the problems that were in the problem set, the first one is you have a supernova remnant with a mass of 4.8 times 10 to the 30th kilogram. That comes out to have a Schwarzschild radius of 7,115 meters. I've illustrated that there with the black circle, but the remnant star actually has a real radius of 12,000 meters. That's illustrated by the blue circle. So this supernova remnant, like a neutron star, has a radius that's larger than the calculated Schwarzschild radius. It is not a black hole, but it is a star. On the other hand, number 2 is you got a supernova remnant that has a mass 4 times greater than the sun's mass. All I did was take 4 times the mass of the sun, or 4 times 1.99 times 10 to the 30th kilogram, get you 7.96 times 10 to the 30th kilogram. And when you put that 7.96 times 10 to the 30th kilogram into the formula for calculating Schwarzschild radius, you get a radius of 11,798 meters. I've illustrated that with the large black circle, and that's the edge of the event horizon. And I made a note in that number 2 that stellar remnant actually has a real radius of 7,500 meters. Is this remnant a black hole? And yes, it is. The actual mass of the object, it would reside within a diameter or a radius of 7,500 meters, and that is a radius for the object that is smaller than the size of the Schwarzschild radius. So things are actually a little bit more complicated than what I've described, but that's the kind of calculation you want to be able to do. All you need to do is compare the actual size of the star to the calculated Schwarzschild radius, and if the size of the star is smaller than the Schwarzschild radius, then it happens to be a black hole. So in number 3, I described the center of our galaxy has a supermassive black hole with a mass that's about 4 million times the mass of the sun. So if you take 4 million times the mass of our sun, it comes out to be 7.96 times 10 to the 36 kilogram. And that gets you a Schwarzschild radius of 1.2 times 10 to the 10th meters. That's, like 1 or 12 billion meters. And the actual let's see. So the Schwarzschild radius of that supermassive black hole, which we call Sagittarius A, has a radius of 1.2 times 10 to the 10th meters. That's the size of the actual event horizon. And I've illustrated that here with that large black circle. Now, this is to scale, and what it illustrates is our actual sun is shown there as the yellow circle. That's the radius of our sun, and its mass is 1 solar mass. But it's a typical star. It's plasma, and the density is not particularly high, but these black holes have a very high classical density. If anything, they have the density of a neutron star, where matter is packed in as densely as it can be. So that black circle represents the size of the black hole in the center of our galaxy. It has 4 million times the mass of our sun, which is illustrated by the yellow circle, but it's only 17 times the radius, only 17 times larger in radius, or 5,000 times the volume. So that should be a pretty impressive comparison. Okay, so anyway, the solutions to that are in the Moodle, and you should be able to work through those problems and see how the comparison works. That's the calculation that you need to be able to do on the Unit 3 exam, and it's the only calculation on the Unit 3 exam. All right, so the topic for this evening was in general relativity and how it relates to gravitational waves. So from Einstein's general relativity, we know that matter causes a dent in space-time, and it turns out that if matter is stationary in space-time, that dent is relatively static. But whenever objects are in motion, that dent in space-time moves around. And that motion of an object within space-time, Einstein and others hypothesized, could cause disturbances that radiate outward as like ripples in space and time. So Albert Einstein hypothesized gravitational waves, that they would exist, but he didn't directly conduct an experiment to prove that they exist, and we only have recent evidence that gravitational waves do exist. And measuring gravitational waves is very difficult, and we can only see events that are very severe. In other words, the motion of the moon around the Earth causes gravitational waves, but we can't detect them here from the Earth. Similarly, if a comet streaks by the Earth, that motion of that comet causes a ripple in space-time, some gravitational waves, but they're too weak to be able to see. So the reason why this is a topic right now in the course is these gravitational waves that we can detect are detected as a result of very severe astronomical events, like black holes merging, neutron stars running into each other. Potentially, if a large supernova were to happen relatively close, we'd be able to detect that as well. Okay, so there are 2 links within this presentation that you should watch. One, a simulation on colliding black holes, and another, a little talk that's illustrated and illustrations about gravity wave events that Brian Cox and another person narrate. Brian Cox is a fairly famous science communicator in physics and astronomy, and a lot of his work is on like the BBC, British Broadcasting Network, and he's kind of famous on YouTube and whatnot. So I invite you to watch those videos. I can't include them in this because YouTube will be like, hey, you're showing other some people's YouTube videos, but watch those videos. So the kind of events that create strong gravitational waves that we can detect are the kind of things like if black holes collide, or if neutron stars collide with each other, or if a neutron star collides with a black hole. They could be objects that are in orbit around each other, or they could just be on a collision course with each other as a result of gravitational attraction. So here's one idea. If you have a surface of a pond or surface of some water, and you talk about points A and B on that surface, if you don't disturb the water itself, the path along the water from A to B is, well, close to a straight line. And the path length from A to B is really like the minimum distance that you could travel from A to B. But if you put a ripple on the surface of water, so like maybe a drop of rock in a position A, and it creates waves on the surface. If you travel along the surface of the water from A to B, the path length from A to B is now longer because you're not just going exactly in a straight line, but you have to go up to the top of a crest of a wave and down into the trough and up to a crest and down to a trough and up to a crest, down to a trough. So what I'm showing in this illustration is that the total length of that red, not really line, but that red shape is longer than the length of the red shape from A to B. Meaning if you take that red shape on the lower part and stretch it out, it turns out to be a larger distance than from A to B. So that's the kind of thing that we think happens in space as well, is that if you have something that's introduced into some area or moves, you can create waves. Now, you can drop a rock into a pond, and that can cause a disturbance on the surface, but you can't just drop a star somewhere into space or make something disappear. But you can create waves on the surface of water by having like a boat move through the water or move your hand back and forth through the water. The presence of an object that's in the water doesn't necessarily make waves unless the object's in motion. Well, the same thing happens in space. It's not so much that the presence of a star or a black hole creates gravitational waves, but whenever that object's in motion, you can end up getting gravitational waves created as a result. So if you have maybe like two neutron stars in orbit around each other, or two black holes in orbit around each other, as they orbit, these waves will propagate out from the location of the objects, and those waves should travel at the speed of light away from the source, making the fabric of space and time change as the waves propagate out. And much like water waves or light waves, the further away you get from the source, the less energy there is because the radius increases over the total place where the energy happens to exist. So the gravitational waves will be the strongest, very close to the motion of the objects, and weaker much further away. So the first evidence of gravitational waves by Joseph Taylor Russell Hulse in 1974. There's a video that I've linked here. You should watch it. It's a short little interview with Joseph Taylor starting at 25 seconds. And here's a picture of Hulse and Taylor. They were awarded the 1993 Nobel Prize in Physics for the first indirect observation of gravitational waves. So what this graph shows is the decay or decrease in orbital period for neutron stars that are orbiting about each other over the course of time. I'll just go back one slide. So if you happen to have objects that are in orbit around each other, they have some energy, but as the gravitational waves propagate out away from the objects, those waves carry energy away from the system. And as a result, the period of time for the objects to orbit about their common center of mass decreases or decays over time. So this shows the cumulative shift or the decrease in energy for the objects orbiting about a common center of mass over the course of time, over the course of, it's a little bit over 30 years in this illustration, as a result of the prediction of gravitational or general relativity. Okay, so the kind of things that would allow us to do direct observation of gravitational waves, this is outlined in chapter 24 in the OpenStax book, is if you have a collision of two neutron stars, a neutron star colliding or being consumed by a black hole, two black holes merging, maybe a type 2 supernova, and the birth of the universe itself. The birth of the universe itself is a whole other issue that will come up later on in the course. But the first four bullet points are the kinds of things that we hope to be able to detect, and we have now detected. So I wanted to mention about this. It's interesting. There was an event that took place just this fall, and it's a gamma ray burst. So we haven't really talked about gamma ray bursts yet, but a gamma ray burst is a burst of energy, of gamma radiation from some kind of a high energy change that happens in our universe. Could be a supernova that explodes, could be neutron star merger. Anyway, the history of gamma ray bursts is very exciting, and whenever we do space-based observatories, I'll tell you more about gamma ray burst. But it turns out that this gamma ray burst it's called GRB 221009A, and that is one way that we classify objects and events that take place in the universe. GRB stands for gamma ray burst, 22 stands for 2022, and the 1009 is October 9th. And then the A actually just stands for it was the first one of that day. Most of them just end with an A because it's not typical to have more than one gamma ray burst that's detected in a day, but they can. So this gamma ray burst was called the BOAT, the brightest of all time. It took place 1.9 billion light years away, which makes it the closest known gamma ray burst that we've ever detected. It's likely that it was a supernova exploding. And the mass of that would be about 30 solar masses. That kind of event would create gravitational waves, but they were too weak to detect. The event is seen by the Swift Gamma Ray Observatory and other observatories based on Earth. I put a little link there to the Swift Mission Control, which is actually at Penn State University at the University Park campus, which is only like an hour away from here. So it turns out that most gamma ray bursts have a particular amount of energy. Some are barely detectable, some are pretty strong. The sensors on board the Swift Gamma Ray Observatory have a minimum sensitivity, but then they also have like a maximum energy that they can take before you like overwhelm the sensor. And the sensor was overwhelmed by a factor of 2. The Swift Gamma Ray Observatory has been in orbit and in operation since 2004. This shows a graph, and it's difficult to understand exactly, but I'll just try to show you like what it means. This shows in gray all of the gamma ray bursts that have been detected since 2008, and this is based upon the Fermi Gamma Ray telescope, which was launched in 2008. So it turns out that toward the left hand of the graph is like the recent time from when gamma ray bursts are detected until the gamma ray energy decays over the course of some time. 10 to the 2 seconds is 100 seconds, 10 to the 3 seconds is 1,000 seconds, 10 to the 4 seconds is 10,000 seconds, and so on. And the vertical axis is the amount of energy from the gamma ray burst. So the cumulative data from all gamma ray bursts happens to all be in the gray, and the bright blue is the detected energy from that one gamma ray burst. It's absolutely completely an outlier. There is no other data anywhere near the blue streaks that are illustrated on that graph. So anyway, the GRB 221009A is also shown here as a visible object taken with the Gemini South Telescope, and that's the Gemini South Telescope, which is in the Andes Mountains in Chile, in South America, and we'll go over that later on in the course. Anyway, those kind of events cause ionization in the atmosphere, and that particular event, here you can see it says on the y-axis like a phase, and don't worry about what that means, but you have these purple kind of jiggity-jaggedy things that's going up and down at about the value of 97. Then right there at 1:20 universal time, there's this massive increase in ionization of the ionosphere for the Earth, and that energy decays. So it turns out that whenever the gamma radiation gets to the Earth, it causes ionization in the atmosphere of the Earth, and that's detectable and that's measurable, and it decays over time. So you see after about an hour, well, I guess this is about 40 minutes from that spike going to the right-hand side, the energy gets back to, typical or average ionization of the atmosphere. Okay, so how gravitational waves are mostly detected. This was a topic a little bit earlier on in the course, or I mentioned it. There's two laboratories called LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. There are 2 locations, one in Hanford, Washington, and the other one in Livingston, Louisiana. They're about 3,000 kilometers apart, and they're shown on that map. The reason for 2 labs is to have some redundancy. Each of the labs can detect vibrations in the Earth from seismic activity, literally from people driving down the road, from any kind of like atmospheric pressure changes, that happened in short term, maybe from an explosion or something. And there's some noise in the data. And in order to tell the difference between the noise and something that's systematic is to compare the data between the two sites. And if you compare the data between two sites and you get similar readings at both places, then it gives you some good information about what's going on. So I put a link here at the bottom for an excellent video done by Physics Girl. And I really want you to watch that video because it's very, very good. And just as kind of an aside, we watched another Physics Girl video earlier. Just in the last week or so, there was an update on her channel that she's struggling with some very serious health problems right now related to long COVID. So you can also watch that. I've always watched the Physics Girls videos and use them in a bunch of different classes because they're just excellent. But she's having a tough time right now personally. That's not exactly why I ask you to watch the video, because I always want students to watch this particular video about gravitational wave observatories. But it just turns out that she's having health problems right now. So hopefully everything works out well for her. Anyway, so the LIGO detector, this is one picture here. So there's this middle laboratory, and then you see going off to the right and to the left, those perpendicular tubes. And those tubes are actually very long vacuum chambers. And those vacuum chambers have mirrors on the ends of them. The tubes are 4 kilometers in length, which is like 2.5 miles in length. And it turns out you take laser light from the main laboratory, send it down each of the 2 arms that are at 90 degrees. The light hits the ends and it comes back. And when it comes back, you compare the return laser light in a technique known as interferometry. And interferometry is a very common optical technique for measuring very small changes or precision motion. It's a very common optical technique in astronomy and also in general metrology. This is the most difficult measurement that humans have ever had to make, though, because what you're looking for is changes in space-time that happen on the order of 10 to the negative 19th meters, which is a 10,000th the diameter of a proton. It's very, very, very small. Basically, if a gravitational wave passes by the laboratory, just like that illustration that I showed where you have points A and B in the pond, where if there's no disturbances in the pond, the path length from A to B is a perfectly straight line. But if you have a gravitational wave pass by the laboratory, or especially through both of them, because they're going to pass through both laboratories, it turns out that the path length between the main laboratory mirror and the mirrors at the end of the vacuum tube, 4 kilometers away, changes just slightly. And you can detect those changes with gravitational wave observatories. So LIGO was first built quite a long time ago in the late 1990s. It operated from 2002 to 2010 with no detection, and the laboratory had major upgrades that took place in the early 2010s by a tune of another $200 million. In 2015, the lab opened back up, and it had a much higher sensitivity than before its operation in 2015. And it turns out that in a way, you could have an event that is seeable by LIGO, but we never had a seeable event in, about a 10-year period. But then with a higher sensitivity, starting in 2015, right away, gravitational waves were observed, and they've been observed a few different times. So there is this black hole merger event, which was in the one video that I recommended, and there's another video coming up too. The top shows data from Hanford, Washington, and it turns out that the left half of the graph from the LIGO Hanford data shows that like up and down kind of waves. That turns out to be the background noise. And similarly, in the middle graph with the Livingston, Louisiana data, there's also those little up and down waves. That's also background noise. But starting about halfway across the graph, you see that there's this regular up and down, up and down, and up and down, and up and down pattern where the wavelength decreases, but the amplitude increases. And then all of a sudden that energy sort of just disappears. So it turns out that what's important is whenever you overlay the data on top of each other, you see on the bottom graph, the left half of the bottom graph has that noise where the graph is dissimilar between the Hanford-Livingston data, but for the right-hand portion of the graph, the data is in agreement, where you have the up and down and up and down and up and down, where the amplitude and the wavelength of any particular portion of the wave over that course of, it's about 7/100ths of a second, illustrates the fact that both of the laboratories saw this gravitational wave event that's measurable, and the laboratories agree based upon having similar data. So it turns out that this represents what we believe are two black holes that merged. One black hole had about 36 solar masses, the other black hole about 29 solar masses. And the black holes merged. When that merger happened, this very strong gravitational wave sequence was sent through space. The point at which they actually caused the merger was when the amplitude on the graphs is the greatest, and it formed a new black hole with about 62 solar masses. About 3 solar masses seems to be missing, and that's energy that, or matter that got changed into energy, and that energy travels away from the merger event out into space. So it's called GW 150914 for gravitational wave event 2015, and then 0914 is September 14th. So it turns out that what we know from that data is that black holes with greater than 25 solar masses can form and do exist, which wasn't really a surprise because we observe incredibly massive black holes like Sagittarius A in the center of our galaxy. And binaries of two black holes can form. So these are two black holes that are orbiting about a common center of mass, and they can merge within the age of the universe. So those are all hypothetically possible. This is just direct observation of it. So we know things are extremely likely to exist in our universe, but we're only certain that they actually happen by direct experimental observation. And as a result of that work, the 2017 Nobel Prize in Physics was awarded to 3 scientists for their work with the LIGO detector. So we've done a couple things about some different Nobel Prizes, and it turns out that even just this evening, some Nobel Prizes in physics are mentioned. There's another merger event in late 2017. 2 neutron stars, each with a mass of 1.1 and 1.6 solar masses, collided. When those 2 neutron stars collided, it was observed by LIGO. It was observed by Fermi, which is a space satellite, which we'll go over, and by the Swift Gamma Ray Observatory. So it was observed as a gravitational wave by a gamma ray observatory and by measuring ultraviolet light. And it's in a galaxy NGC 4993, which is about 130 million light years away. The next generation of gravitational wave observatories is hoped to be one that's in space. So it turns out to increase the precision of the measurement, you want to get rid of that noise. And how you get rid of the noise is to get rid of vibration. And one way to get rid of vibration is to put something not on the Earth, send it up into space. And you can also increase the baseline of the laser beam legs from 4 kilometers to kind of as big as you want. So this illustration shows a proposed gravitational wave observatory called LISA, the Large Interferometer Space Antenna. And it was originally a project between ESA, which is the European Space Administration, and NASA in the United States. But the funding for it has been slow to come, and it's unlikely to be funded by NASA. So the current plan is that ESA will launch something like LISA somewhere around 2037, hopefully being able to detect gravitational waves from other types of events that are less severe and measure them more frequently. Anyway, there's a little review of general relativity toward the end of the thing that you should look through. And that's kind of a review of general relativity, black holes, evidence for black holes, and whatnot. Anyway, So if you missed class, hopefully that was helpful to go through some things, and whatever questions you got, just let me know. But I wanted to make sure that if you didn't make it to class because you had to leave for break or something was up, that you were able to hear from me a little bit about what is in the slides. All right, take care.